Hello, everyone. My name is Grecco Oyarzun. I am a postdoc at Johns Hopkins, where I work with Mark Rafelsky, who himself is at Space Telescope, and the other people you see here listed. And we're all part of the MANGOS collaboration, where we do exactly that. So we use H1 gas absorbers, in particular damp Lyman alpha absorbers, to constrain galaxy formation at high redshift. So let me start by defining what a damped Lyman alpha absorber is to those who are unfamiliar with the subject. So when you take a quasar at high redshift and you take high resolution spectroscopy of the quasar, you see that blueward of the Lyman alpha emission from the quasar, there's all the intervening H1 gas in the universe is going to leave absorption signatures. And most of that gas is low column density gas. So gas in the intergalactic medium that's leaving these low equivalent weight features that we see, and we call the Lyman alpha forest. Now, occasionally you'll see some very prominent absorption features, like the one pointed in here with the red arrow, and that's an example of a damped Lyman alpha absorber. So in short, damped Lyman alpha absorber is a high H1 column density intervening gas absorber that's apparent in the spectrum of a background quasar. So now the follow-up question is, well, why should we care about damped Lyman alpha absorbers? So first, because they dominate the H1 mass density of the universe. So if you care about H1 gas, then most of that gas is traceable by damped Lyman alpha absorbers. And even though they are rare compared to this low column density gas in the Lyman alpha forest, because of their high H1 column density, they turn out to dominate the H1 gas mass density. And because of that reason, we believe that damped Lyman alpha absorbers trace the H1 gas reservoirs of galaxies at high redshift. So if you're interested in the baryon cycle and studying the baryon cycle in galaxies, then damped Lyman alpha absorbers are your observational window to studying that H1 gas. And finally, you notice here that redward of the Lyman alpha emission from the quasar, there's also metal line absorption that's imprinted. And with damped Lyman alpha absorbers, we can actually use those metal absorption lines to actually understand and trace the chemical content and the metal enrichment of H1 gas at redshifts greater than 1 or 2. So hopefully I have convinced you that damped Lyman alpha absorbers are interesting and useful. And because of that reason, there's been efforts for decades to try to understand and identify the galaxies associated with these absorbers. So if you notice here, between 1990 and 2014, there have been numerous studies attempting to identify the galaxies associated with these systems. And in those 24 years, only 9 associations were established. That low detection rate suddenly changed in 2014 with the advent of ALMA and MUSE, which basically what they allowed us was to look for the galaxies not necessarily at the exact location of the quasar or projected location of the quasar, but rather at larger impact parameters. So say up to 100 kiloparsecs away from the quasar. And that ability enabled studies in the last decade to find 3 times as many galaxies as we had been able to find previous to 2014. So basically, this is ALMA and MUSE enabled us to identify galaxies that were at projected separations from the damped Lyman alpha absorber. And another instrument that can allow us to identify the galaxies with these systems is KCWI. So this year, we published a paper that precisely did that, used KCWI to search for the galaxies associated with 14 damped Lyman alpha absorbers at redshift 2. So these were observations that took place in 2019. So we took advantage of, at the time, which was the main feature of KCWI, which is to be very sensitive in the blue, which if you're looking for these galaxies in Lyman alpha emission, that means redshift 2. So for our sample of 14 DLAs, we detected 5 galaxies, which you see the Lyman alpha emission from the galaxy plotted up on top. You actually see, you can see 6 emission lines. So the last one here is a tentative detection. And at the bottom here, you can see the image you can construct from the data cube showing the detections. So the red crosses in each one of these panels shows the location of the quasar, and of course of the damped Lyman alpha absorber. And in a black circle that I don't know if you can spot, shows the location of the Lyman alpha emitter, the galaxy that we have associated with the quasar. So you can see that, for example, for these 3 systems, the quasar and the Lyman alpha emitter are pretty close to each other in projected separation, so within 10 kiloparsecs or so. But for these 2 systems over here, we actually see that the quasar is here, then the galaxy is up here. Or this is the same system, it's just 2 different galaxies. So, and then the quasar is here, and the Lyman alpha emitter is out here. So that's why integral field spectrographs allow you to do. And these galaxies are out to between 50 to 70 kiloparsecs away from the quasar. This system is actually very interesting because the star here shows a galaxy that emits in CO that was detected with ALMA. So damped Lyman alpha emission and the follow-up with integral field spectrograph and ALMA allows you to identify systems that can constrain the baryon cycle. You have your H1 gas that's probed by the DLA. You have 3 galaxies identified in CO emission and in Lyman alpha emission. So if we move further, I want you to pay attention to this figure in which we're plotting our detections in Lyman alpha luminosity on the y-axis against the metallicity of the absorber. So you can think of this as like how metal rich the H1 gas is in these systems. And the main feature here is that if you look at the highest metallicity DLAs in our sample, we only get non-detections in Lyman alpha emission. So basically what this means is that there's an absence of bright Lyman alpha emitters in the vicinity of high metallicity H1 gas at redshift 2. That's the main takeaway of the paper. And our interpretation for this result is that high column density metal rich H1 gas at redshift 2 is likely associated with galaxies that are not bright in Lyman alpha emission. And our preferred scenario for a galaxy like that is a galaxy that's very massive, that's very dusty, and therefore any Lyman alpha photon production from these galaxies is being absorbed by all the dust in these systems. So now I'm going to use the final minutes that I have to talk about what we're doing now. And basically what we're doing is we're taking advantage of the new capabilities of KCWI, which is the installation of the new and the red arm. And what it effectively means for this kind of research is that we can push the sensitivity in detecting Lyman alpha emission up to redshift 5. And in particular, what we're doing with our new survey is we're taking advantage of quasar sightlines that contain multiple DLAs. And this is the benefit of performing a study like this from the Northern Hemisphere, because for historical reasons, samples of DLAs and quasars and in high resolution, where all the metallicities and the column densities are greatly characterized, those were performed from the Northern Hemisphere. And therefore, we can target large samples of quasars and DLAs that we cannot do from the South. So this survey is actually targeting 21 quasar sightlines that are outlined here. These are all the different quasars. And the x-axis shows wavelength that contain multiple DLAs each. So by targeting 21 quasar sightlines, we can attempt to detect Lyman alpha emission around 49 DLAs in total. So this is part of a program that has been awarded so far 6 Keck nights, of which 4 have already been observed, and that have yielded so far 13 detections in Lyman alpha around 31 DLAs. You'll see some of these detections here with the redshifts of the emission and of the absorption shown at the top of each panel. So now we're going to start putting these detections in some scaling relation plots. So all these figures show redshift on the x-axis, and the y-axis show DLA metallicity, H1 column density, and the impact parameter of the galaxies. And the different symbols show in black what we found at redshift 2. In blue, everything that's been done in the literature up to date using Lyman automation. And in red, what we've achieved in only 4 nights so far with the red arm of KCWI. And you can see that we are almost at doubling the total amount of detections that have been done by multiple works in the literature. And after the survey is complete, we're on track to more than doubling the total number of associations beyond redshift 3. And yeah, so this is basically going to be essential in our efforts to build these samples of absorbers and emitters that constrain the connection between H1 gas, galaxies detected in emission, that are key to constraining the baryon cycle in observations. So with that, I'll stop and take any questions. Thank you.